Namaste, my friend, and welcome back to JEE Physics with Typical Monk. This is Class 8, and today we meet the force that never switches off. Every mass in the universe pulls on every other mass. The apple falling from the tree and the moon circling the earth obey the very same law. When Sarah first met this chapter, she mixed up the formula for G at a height with the formula for G at a depth and lost a full mark for a mistake that takes 30 seconds to avoid. Today, we fix that, and we build the whole architecture properly. The force, the field, the potential found through calculus, escape, and orbital velocity, and Kepler's laws of the sky. And here is why this matters more in G than in NEET. G expects you to derive the potential by integrating the field, not merely code it. Take a slow breath. Let us begin. So what will you carry home from today's class? First, Newton's law of gravitation and the gravitational field it creates, the inverse square force, written properly as a vector. Second, the gravitational potential found not by memory but by integrating the field, V equals minus gm over r, the calculus step that G demands and NEET skips. Third, exactly how G changes with height above the surface, with depth below it, and with the spin of the Earth itself. Fourth, escape velocity and orbital velocity, and the fixed ratio that quietly connects the two. And fifth, Kepler's three laws, the energy carried by satellite, and the special case of a geostationary orbit. Ready? One idea at a time. Let us start with the law itself. Newton's law of gravitation. Any two masses attract each other with a force Gm1 m2 over r squared. Same G everywhere in the universe, from a falling apple to two orbiting galaxies. Now divide that force by the mass being pulled, and you get the gravitational field. G equals gm over r squared, a vector that always points in toward the source mass. Here is the calculus idea. The gravitational potential is the negative integral of the field with respect to distance, integrate g dr, and out comes B equals minus gm over r. This is exactly where G steps beyond NEET. And multiply potential by the mass placed there, and you get the gravitational potential energy, U equals minus gmm over r, always negative, and exactly zero only when the separation is infinite. Look at this picture carefully. It carries almost the whole chapter in one glance. Two masses, separated by a distance r, pull on each other with force gm1 m2 over r squared, inverse square, always, whatever the two masses happen to be. Now follow the curve inside the Earth. Only the mass enclosed within your own radius actually pulls you there. So as you go from the center outward, G rises in a straight line, reaching its largest value exactly at the surface. Step outside the surface, and the entire mass of the Earth behaves as though it was squeezed into a single point at the center. So G now falls as 1 over r squared, the same law we started with. David used to think G simply gets weaker with distance in some vague way. The day he saw this curve, rising to a peak at the surface, then falling as 1 over r squared beyond it, he never confused height and depth again. Now let us pin down exactly how G changes, because G loves to test this precisely. For height above the surface, when the height is much smaller than the Earth's radius, G prime equals G times 1 minus 2h over r, the drop is twice the fractional height. For depth below the surface, G prime equals G times 1 minus t over a plain straight line, reaching exactly 0 at the very center. And because the Earth spins, the effective G at the equator is reduced by omega squared r, the centrifugal contribution, while at the poles it is barely touched at all. Lisa once used the depth formula for a height problem in an exam and watched the whole answer collapse. Remember, the height formula halves the drop. The depth formula is simply linear, and they are never interchangeable. Time to solve a full G numerical together, slowly, the monk's way. A satellite orbits the Earth at a height equal to the Earth's radius itself. Take the Earth's radius as 6,400 kilometers. That is 6.4 times 10 to the 6 meters, and surface gravity as 9.8 meters per second squared. Find the orbital velocity, the escape velocity from that same orbit, and the total energy of the satellite. Step 1. write down what is given. R equals 6,400 kilometers. G equals 9.8 meters per second squared. The height h equals r, so the orbital radius r equals 2r. And remember the useful substitution gm equals gr squared. Step 2. The orbital velocity. V orbital equals the square root of gm over r, which becomes the square root of gr squared over 2r, which simplifies to the square root of gr over 2. Walking the numbers gives 5,600 meters per second or 5.6 kilometers per second. Step 3. The escape velocity from that same orbit, not from the surface. V escape equals the square root of 2dm over r, and by the algebra, this is always root 2 times the orbital velocity at that radius. So 5.6 times root 2 gives 7.9 kilometers per second. Step 4. The total energy. E equals minus gmm over 2r, which simplifies here to minus grm over 4. Notice the sign, negative, for every satellite that is truly bound to the Earth at every possible radius. Step 5. Gather the answer. Orbital velocity 5.6 kilometers per second. Escape velocity from that orbit 7.9 kilometers per second. And a negative total energy confirming a bound orbit. Given orbital velocity, escape velocity, energy. The same 4 moves solve every satellite numerical G can throw at you. Now, the shape of the orbit itself and the energy hidden inside it. Kepler's first law. Every orbit is an ellipse, and the central body sits at one focus of that ellipse, never at its center. Kepler's second law. The line joining the satellite to the focus sweeps out equal areas in equal times, which is exactly why a satellite moves fastest when it is closest to the focus and slowest when it is farthest away. Kepler's third law. The square of the time period is proportional to the cube of the orbital radius, with the very same constant of proportionality for every satellite orbiting the same central body. And the energy split that ties it all together, kinetic energy, is positive and equal to gmm over 2r. Potential energy is negative and twice as large in size. So the total energy comes out negative. And that single negative sign is the mathematical reason the satellite never drifts away. Now sit up straight. These 5 lines are what G actually asks, year after year. 1. Escape velocity depends only on the planet. B escape equals the square root of 2gr, and never on the mass of whatever is trying to escape. 2. Compared at the same radius, orbital velocity and escape velocity always differ by exactly a factor of root 2. Memorize that ratio cold. 3. The height formula and the depth formula for G are never interchangeable. One halves the fractional drop. The other is a plain straight line to 0. 4. A geostationary satellite has a 24-hour period, sits in the equatorial plane, and orbits at about 6.6 times the Earth's radius. 5. A bound satellite always carries negative total energy. Zero energy means it just barely escapes, and positive energy means it never comes back at all. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one. Assertion. The gravitational potential energy of a satellite bound to the Earth is always negative. Reason. Potential energy is chosen to be 0 at infinite separation, and gravity does negative work as the separation shrinks from infinity. Check each statement, then the connection. Is the assertion true? Yes. Is the reason true? Yes. Does the reason explain the assertion? Perfectly. That choice of 0 at infinity is exactly why every closer, bound configuration reads negative. Both true. Reason explains. Option A. Second one. Assertion. The weight of a body becomes 0 at the very center of the Earth. Reason. The gravitational field intensity increases in a straight line with depth below the surface. Pause on the reason first. It says G increases with depth, but we just learned G decreases in a straight line with depth, reaching 0 at the center. So the assertion is true, but the reason as stated is false. Assertion true, reason false, option C. This is the trap that catches John every time. Third one, assertion, the escape velocity of a rocket depends on the mass of the rocket. Reason, escape velocity equals the square root of 2 gm/r, a formula with no trace of the escaping body's mass in it. Check the reason first. Completely true. The formula truly has no mass of the rocket in it. Now the assertion, since the formula has no such mass term, escape velocity cannot depend on it, so the assertion is false. Assertion false. Reason true, option D. A quick match now. Say each formula aloud before I reveal it. Escape velocity, root 2 gm/r. The speed needed to leave forever. Orbital velocity, root gm/r. The speed needed to keep circling. Gravitational potential, minus gm/r. Work done per unit mass. Brought in from infinity. And Kepler's third law, d squared proportional to r cubed. The same rule for every satellite of one body. If all four came to you before the reveal, this chapter is becoming yours. Use a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. Gravitational potential energy becomes less negative as a satellite is raised into a higher orbit. Hold your verdict. Statement 2. A geostationary satellite can be placed above any city on the Earth's surface. Think about which plane a geostationary orbit must lie in. Statement 3. The orbital velocity of a satellite does not depend on the satellite's own mass. Recall the formula and check what cancels. So, how many are correct? Two statements, the first and the third. Rising to a higher orbit truly does make the negative potential energy less negative, and the orbital velocity formula genuinely has no trace of the satellite's own mass. But the second one falls. A geostationary satellite must sit in the equatorial plane, never above any arbitrary city. Two correct, and the middle one is the trap. Now let me save you some marks. Two myths that trap thousands of students every year. Myth 1. G increases as you go deeper into the Earth because you are getting closer to the mass sitting below you. It feels so natural. Surely closer means stronger. But here is the truth. G actually decreases in a straight line with depth, because only the mass enclosed within your own radius pulls you. The shell of material above you contributes nothing at all. Myth 2. Escape velocity and orbital velocity are simply the same speed for a satellite skimming just above the surface. The truth, they differ by exactly a factor of root 2 at that same radius. Orbital speed alone keeps you circling forever, but it can never, by itself, let you leave. Time to test yourself, rapid fire, and every answer today is a number. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just what you built today. Question 1. What is the escape velocity of the Earth, taking g as 9.8 meters per second squared and r as 6,400 kilometers? 11.2 kilometers per second. Question 2. What is the orbital velocity of a satellite skimming just above the Earth's surface? 7.9 kilometers per second. Escape velocity divided by root 2. Question 3. What is g at a depth of r over 2 below the surface? Exactly g over 2 from the straight line depth formula. Question 4. What is g at a height equal to the Earth's radius? Using the exact inverse square law rather than the small height approximation. G over 4, since the distance from the center has doubled. And question 5. The thinker. What is the time period of a geostationary satellite? 24 hours, matched exactly to the Earth's own rotation. If you answered all 5 before the reveal, you have truly understood today's class. Let us gather the whole class in one slow breath. Newton's law gives the inverse square force, and integrating the field it creates gives the potential. Gm over r squared becomes minus gm over r through calculus. G changes with height, with depth, and with the Earth's own rotation, and the height formula and the depth formula must never be swapped. Escape velocity is always root 2 times the orbital velocity, whenever the two are compared at the same radius. Kepler's 3 laws. An ellipse equal areas in equal times, and t squared proportional to r cube govern every satellite, whether it is a moon or a man-made machine. And the total energy of a bound satellite is always negative, zero at the edge of escape, positive once it is truly unbound. And next class, we turn from the pull of gravity to the push and stretch of solids themselves. Elasticity and mechanical properties, stress, strain, and Hooke's law, treated with the calculus of a stretching rod. Do not miss it. And so, my friend, from an apple falling off a tree to a satellite that never falls at all, you now hold the one law that quietly connects them both. Every escape velocity, every orbital speed, every satellite's silent negative energy, all of it traces back to the single inverse square law you mastered today. Sarah, David, Lisa, and John all started exactly where you are right now with this one class. Be patient with yourself. Tonight, revise the 2G variation formulas once, slowly. Height halves the fractional drop. Depth is a plain straight line to zero. One idea at a time. You will crack G. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you among the stresses and strains of solids.